Okay, here we are. This is the second video lecture for Physics 2A. Physics 2A, video lecture number 2. Start with some announcements. I have sent out a revised syllabus to everybody, both sections, and a couple of points to make again. The homework, I want to see handwritten notes turned in, and I gave some dates for it. Basically every Friday, excluding the spring break Friday, every Friday I put the dates on the syllabus. I want a nice picture, and you can lay a bunch of them on the table and take that picture, because in the course of a week you'll generate a fair amount of notes. Okay, I want to see that you're taking those notes, so that's really the most important thing, that you take the notes, look at the video a second time, and really learn the stuff. And by the way, I've had a couple of notes already sent in, and they were excellent. Okay, so you can easily make notes that are better than what I'm putting up here on the board, because you've got some time and you've got a lot of space. Leave plenty of space in your notes and make the most of them. Then I said something about the exams. This is where it's going to get interesting. There is a free app from Adobe that will convert pictures to PDF files. And when it comes to the exams, that's what you'll want to send me, a PDF, because you can imagine I'm sending you the exam by email. You're taking the exam, you get more time than just an hour. Okay, so you take the exam, and then you want to send it back to me. And I get these exams, and they have to be nice and readable to me. I print them out and put a staple in them and start stacking them. And I will have 170 of them. Okay, two sections, different exams of course, but it's going to be a lot, 85 in one class, 80 in the other. It's going to be quite a few exams. So, but we're going to make it work. Okay, I'm confident that if we get up to speed here, I'm putting the material in these lectures to make it so that you can pass these exams. Okay, good. And the lab policy will be sent out separately. For my section, I'm actually a little bit behind on that, but we're going to get up to speed on that too. Okay, so what we're doing today is to review the homework problem, in particular this one here with the escape speed. Then we're going to review the torque concept. We already did the torque concept in chapter 8 for that one lab. We'll review that again. And having reviewed that, maybe a couple homework problems will come out of that as well. Then we'll go to Newton's law for rotation. I think in next lecture after this, I'm going to have to be in the lecture hall and show you guys some demos. But right now we have it here in this nice studio of mine. Okay. So let's get started. Okay. So chapter 7, problem 39. See, what we're looking at was a launch from a central body of radius r. We're going to fire this thing up at a certain speed, and it's going to come to a stop up here at point B. So yeah, we know that is an energy problem. And just building on what we had last time, EA equals EB, 1/2 mVA squared, because that's the kinetic, plus the potential, over R sub A. Remember, potential energy has that minus sign in front of it. It's coming to a stop. There will be no kinetic energy, but there will still be this other potential energy, R sub B. So the next step is to put in what we had. We had 1/2 m, 1/3 of the escape speed squared, minus g m over R sub A is equal to minus g m over r sub b. And by the way, this r sub a, now we can say that was the actual radius that we were at, the radius of Earth. Now here it gets interesting. I'm going to have 1/2 m. I'm going to have 1/3 squared, so that's 1/9. And I'm also going to have the escape speed squared, which is 2gm over r for this central body. Minus gm over r equals minus gm over r sub b. And r sub b is what we're looking for. So the only unknown here is going to be r sub b. We're going to get some cancellations. 1/2 against 1/2 here. We have gm over r times 1/9 minus, that's not a cube, 1/9 minus 1 equals lowercase m there as well, minus gmm over r sub b. Okay, what cancels? G both m's. And if I get rid of this minus sign here, well, let's leave that right there for a moment. What we're left with is 1/9 minus 1 times 1 over r, that's the left side here, 1/9 minus 1 and 1 over r equals minus 1 over r sub b. I'm going to put a box around here because at this point we really have the answer. Okay, we're right there. Actually, having set it up right here, we're all good to go. So 1/9 minus 1 minus 9/9 is negative 8/9. So I'm going to have 8 over 9r is equal to 1 over r sub b, and I'll just invert that. Here's our answer. Go ahead and put the answer up here. These guys have written this down already. So we have r sub b is 9/8 times the radius of Earth. Okay, so 1/3 of the escape speed took us up a ways, but maybe not that high. 1 1/8 Earth radii. Okay. Now again, the key to all of these energy problems, and I definitely want to give you something like this on the next exam and maybe even on the final. The key to all of these was that first step, E sub A equals E sub B. From there we just did step by step. Okay. So that's a very important problem, and problems of that type, we want to be able to set them up and then take them out to the answer. Good. Let's also look at a torque problem. So here I'm going to write chapter 8. Torque. And I'm going to put this up as homework. Problem such and such. Let me put a couple up here right away. Right, 4, 18, and 25. And I'll do this often. I'm going to work these, right? I haven't written it up as a homework problem. I'm going to do them, or at least get started. for problem 4, we're looking for the net torque on a wheel. So imagine you've got a wheel and an inner hub here. So there are 2 different radii, and you have forces attached to these, and it's going to be able to rotate about this axis coming right out of the board. So we have a force here, and they give some angle there. We have a force here, and the third one is like this. So we want to find the net torque. And remember, torque is a twisting force. So these 2 here, I'll just call them, what are you going to call them anything? I'm just going to call them A, B, and C. These are forces. These 2 are causing it to go clockwise. This one here is causing it to go counterclockwise. But what makes this problem easy, they'll give you some values on these, is that the angle that they threw in there is actually irrelevant because the torque is a force per lever arm, and we always have, oops, this one goes here. We always have a perpendicular lever arm because we're just acting at the edge of these spools here. Think of it as a string around a spool. Okay. So the angle that they put in there is actually a bit of a decoy. We don't need it. We just have F sub A, R sub A, counterclockwise minus F sub B, R sub B minus F sub C, R sub C. These are all just force times lever arm, force times lever arm on all 3 of those. So that's a good reminder of what torque is. You get it twisting counterclockwise, got it twisting clockwise. Okay. And 25 I'm also going to do. Chapter 8, torque. So we just talked about 4. Talked about 25. I'll leave 18 for you guys to think a bit about. So problem number 25 is just a sign hanging from the wall. And based on what they give us here, I'm just going to write ice cream. I think that's what they call it. It's an ice cream sign hanging from here. And we want to suspend it, or we want to reinforce this with a cable. And they gave us this angle here. So what we have is a center of mass in the ice cream sign, which has to be right in its center. Call that M, G, and then the center of mass of the beam itself, MG. So there are 2 different lengths, 2 different distances. We're going to measure the torque right there. And then we've got a tension in this cable. Okay. Now, unlike the problem that we had, and this is just a wall that we're butting against, unlike the problem that we had in the lab, we've placed the angle a little bit differently here. So we're going to have tau counterclockwise right here. The one that gets the plus sign is going to be T cos theta. Okay. T cos theta times the full length. T cos theta times the full length of the beam there, because that's where this is acting at. Okay. And the clockwise torques will be the respective masses and their respective distances from from the pivot right here. I'll write pivot right there. Okay. So you've got the clockwise ones, and then of course net torque is going to equal 0. Problems like this are kind of nice. They allow you to often solve the entire problem, say, of finding the tension just with the torque equation. The force equations would be needed to solve for the reaction forces there. Okay, so in fact, for problem 25, I'm just going to say part A. Okay. Part B is to get the reaction forces as well. That we can also do if we need to. Okay, so that's basically the review that we had on the torque concept. Torque is force times lever arm. Torque is a twisting force, and tau FR, and what you remember, force times lever arm. It goes back to the whole wrench that I drew up on the board that time, the wrench, and basically our experience with hand tools helps us out with the understanding of torque. Okay, so that was review. And I want to get to something new now. So you've got this, I'm going to erase this. And that is, so next, torque and rotational dynamics. Okay, torque and rotational dynamics. So let's write this down. Torque and rotational dynamics. Okay. Yeah, when we say dynamics, we're talking about Newton's law. Okay. And so what we're going to consider is spinning something. Remember the wheel I had in class? I give it a twist and it rotates. Okay, and the twist is the application of the torque, and the rotation is the result of that application of the torque. So we're going to apply Newton's law in the following situation. Imagine there is a single point M here at a distance r from the center, and we know there's a circular motion formalism. Now what we're going to imagine is that we are applying a force tangent to the wheel. Okay, and of course that's going to cause it to spin up. Going to cause it to spin up. So we could say F equals m times acceleration. That would be Newton's law. But it's a tangent force, and so it's a tangent acceleration. We're not talking about the centripetal, not the centripetal, but just the tangent acceleration as this thing accelerates in the direction of the force before spinning around. Next, we're going to multiply tangent force times r, mass acceleration sub t times r. Okay. And here's the crucial next step. This is a torque, force times lever arm. M, now the tangent acceleration is alpha r. That was back from our rotational dynamics. Actually, that was from our rotational kinematics, pardon me. Rotational kinematics. Acceleration is alpha r, multiplied times r again. Okay. Need a little more room here. So that's spinning this disc up. Keep this on the board. Now let's look at what we have here. take this up here, we have torque equals mr squared, I'll put this in parentheses, times alpha. It's more, there we go, times alpha. And now let's consider the entire wheel that we were spinning. Consider the entire wheel. With the entire wheel, we're going to have net torque is the sum of mr squared for the entire wheel, but alpha is the same for the entire wheel. And this is Newton's law. So I got it just by multiplying and plugging in some definitions. And what I have is tau equals, I'll just repeat this, sum over mr squared alpha compared to F equals MA. Okay. Let's compare these two. There's an analogy because this is the angular acceleration, this is the linear acceleration. So what's in parentheses here must be taking the place of the mass in Newton's law as we originally learned it. And this quantity here is referred to as the rotational inertia or the moment of inertia. So moment of inertia gets the letter I. It's the sum of all the masses times their distances squared. And these distances are the distance, so I'm going to put some little subscripts. Summation, distance from the axis of rotation. So R sub I equals perpendicular distance from the axis of rotation. Distance from the axis of rotation. So this moment of inertia is a really interesting dynamical quantity. I'm going to have to show you some demos in the lecture hall to bring it to life, so to speak. It is, well, maybe, you know, if I had my ruler, I can show you anything with a ruler. Let's see here. This is a small version of what we'll have as a demonstration later on. Yeah, I've got a ruler here, okay? That's not impressive, 30 centimeters. But I can rotate this thing about an axis. There's an axis through the middle, it's rotating like a propeller. I could also rotate it around a lengthwise axis here. I could rotate it about an axis held in the end. And even with a ruler, but especially with a meter stick, you're going to feel substantial difference in the resistance to rotation. Okay, so I'm going to end this lecture with a little more discussion of this moment of inertia, and I hope to show you some better demonstrations of this. I'll bring this operation to the lecture hall. So moment of inertia we'll call that the resistance to a twisting force, which is to say force, i.e. a torque. Well, you apply a twisting force, and the more moment of inertia, the more torque you have to put into it, the more you feel that resistance. And next time we spend some time looking at the definition, we're going to see it's this quadratic dependence on the distance from the axis that makes all the difference. So what are the units of this thing? The units are kilograms times meters squared. Kilograms times meters squared. Okay, we're going to leave it right here. Next time I'll get you some demonstrations of this and we'll do some actual applications of Newton's law for rotational motion. Okay, good.